Here we're going to look at two different types of graphs, continuous and discontinuous. So first we're going to focus on continuous. So a continuous graph is a single unbroken curve that you can draw without lifting your pencil from the paper. So here we have four different graphs. So let's look at graph number 1 first. So graph number 1, if I were to draw this graph and follow it with my pencil, I do not need to pick my pencil off the paper in order to complete this drawing. It's one fluid motion. When I look at graph 2, again, here I have a linear, so I have a straight line. If I draw the line and I follow it with my pencil, I do not need to pick my pencil off the paper. In graph 3, even though this graph looks a little weird because there's flat pieces and there's curves, I can still follow the shape of this graph without picking my pencil off the paper. And for graph number 4, we have a circle. If I draw this with my pencil, I don't need to pick it up off my paper. So these are all examples of continuous graphs. From last class, we talked about functions and how a function is something that passes the vertical line test. So if I draw vertical lines on my graph, if it passes the vertical line test, it's a function. So not all continuous graphs are going to be continuous functions. If I look at graph number 1 and I draw vertical lines, okay, this does pass the vertical line test, so graph number 1 is a continuous function. Graph number 2, again, passes the vertical line test, so that is a continuous function. Graph number 3, again, passes the vertical line test, so that is a continuous function. When we get to graph 4, though, when I draw a vertical line, it fails the vertical line test because we have two different points that are on this line that have the same x value, so that means it's not a function. So graphs 1, 2, and 3 are continuous functions, and graph 4 is just a continuous graph. The opposite of a continuous function is a discontinuous function. Discontinuous function is a function that is not a continuous curve where you need to pick your pencil off the paper to draw it. So here in graph number 1, okay, we have a linear. However, you can notice there's a hole right here. So I'm just going to circle it again. So over here, there's a hole. It's an open circle. So it's continuous to a point. So I'm following this graph and I get to the hole. I have to pick my pencil off the paper, jump over the hole, and come out the other side. In graph number 2, okay, I have 3 pieces to my graph. So I draw the first piece on the left, pick my pencil off the paper, draw the bottom, pick my pencil off the paper, draw the right. And then in graph number 3, I have a piece of my curve here, pick my pencil off the paper, continue drawing it down here. So these are 3 different types of discontinuities. So in the first graph, we have a hole. Okay, that's the only discontinuity, is that there's a hole. And the second one, we have a jump discontinuity. So it's going from one piece, we have to jump to the other, then we have to jump to the other. And then graph 3 actually has both. It has a hole and a jump. As you can see here, there's a hole, and then we jump to the next piece. So here are some examples. We have 2 graphs. We want to see, are they continuous or discontinuous? And then we want to find the domains and the ranges. So again, just kind of like a refresher from last class. So in this first graph, okay, if I try to draw it with my pencil, I don't need to pick it up off the paper. So this is a continuous graph. So I'm just going to write that it's continuous. And then we are going to find the domain and the range. So the domain, I'm just going to put a D for domain. Remember that the domain are the x values. So if we're looking at the x values on this graph, the arrows are indicating that this graph continues. So as it continues, it's going to span every x value that there is. So it would be all real numbers. So in set notation, we have x such that x is an element of all real numbers, or we can say in interval notation, negative infinity to positive infinity. So I'll put or here. So set notation and interval notation. For the range, we're looking at the y values. So again, we have these arrows at the ends. So that means that the graph is extending up and down infinitely. So again, every single y value will be a part of this graph. So in set notation, we can say y such that y is an element of all real numbers. Or if we're using interval notation, again, we can just say negative infinity to infinity. In the second graph, okay, here we have a piece that we're drawing. We have to pick up our pencil from the paper and then finish the graph. So this is discontinuous. And now we're going to try to find the domain and range. And the domain, again, I'm just going to call it D. So here we have endpoints. We can see that this does not extend in both directions. So from left to right, we're starting at -5, and we're going to 5. Now, even though that there's this gap here, there's this jump in the graph, if we notice the closed circle here at 1 and the open circle at 1, that still means that 1 is part of our function. So it's included in this piece, but not in this piece. So when we're dealing with our domain, it's every x value between -5 and 5. So just be aware of these open circles and closed circles. So as long as it's a closed circle, it's including it. So for our set notation, we can say that x such that -5 is less than or equal to x, which is less than or equal to 5. Or in our interval notation, because we have included closed circles, we're going to use our brackets. So it's -5 to 5, close our bracket. For the range, we're dealing with the y values. So our lowest y value we can see right here is at -1 for y. And for our highest y value is going to be about here. So that's about 3.5. So for our set notation, we'll say it's y such that -1 is less than or equal to y, which is less than or equal to 3.5. Okay, and we're using less than or equal to because there's no open circle here, so it includes those numbers. Or if we're doing interval notation, we can say square bracket from -1, comma, 3.5 bracket, because it's including. Something that we want to make a note on is that parts of the graph can be continuous. So if you're asked about continuity on a specific interval, the answer may change. So here's the same example from the slide before. Now, if they're asking, is the graph continuous on the interval from -5 to 5? No, right? This is not continuous on the full interval because we have this jump at 1. Is the graph continuous on the interval 1 to 5? Now, notice this interval here. The 1 has a parenthesis, meaning it's not including 1, and the 5 has a bracket, meaning it's including 5. So if I'm looking at just between 1 and 5, I'm looking at this upper piece that starts with the whole because it's not including 1. So in this piece, is that continuous? Right? Yes, it is, because I can draw this without picking my pencil off the paper. So even though the overall function is discontinuous, if I'm asked for a specific part of the domain, it can be continuous. So here, yes, it is continuous. What about on the interval from 1 to 5? Inclusive. So notice again the brackets on 1 and 5. So if I'm including 1, I'm including this point here. So from this point and this piece of the graph, is that continuous? No. So we want to make sure that we're paying attention to the types of brackets that we have.